query lanes, dedicated resources for high priority queries, and avoids short and fast queries waiting for long running queries. So that is why, let me go to the previous slide. That is why the graphic we have is a graphic of a carpool lane. The idea is that with query lanes, you have regular lanes, and then you have high priority lanes. And the high priority lanes are like a carpool lane, dedicated space that is only available for your high priority traffic. Just like a carpool lane, high priority traffic can use the regular lanes as well, but they don't have to. They have a special one just for them, and reserving it for them enables them to get the best quality of service. So here, I want to talk a little bit about the problem today that query laning is meant to solve. So we have a concept in Druid today of query prioritization, but the query prioritization concept in Druid only affects CPU use on the Druid historical servers. So it ensures that they all get, that a high priority query gets priority for CPU time slices on historical servers. But what it doesn't, what query prioritization previously to Druid 018, did not help with is resources that are higher level than that. So, and specifically resources that limit the number of concurrent queries. So the one I want to talk about now, the one that query laning is designed to help with, is Druid server threads. So the problem that we're solving is that each Druid query requires one thread on the broker to handle. And this is something that's been the case in Druid since the beginning and still remains the case. Every Druid query requires one broker thread. There's a limited number of threads. It's given by this Druid server HTTP num threads parameter. It's usually on the order of a few dozen per broker. So the idea being that per broker, 40, 50, some odd queries are able to run concurrently. This thread is used. It's tied up handling that one query from the moment that the user is connected to the broker until results are returned to the client. And the issue that can happen is on a large cluster with heterogeneous workloads, where you have some workloads that are interactive and some workloads that are reporting based. These long running queries can potentially use up all the connections. Let's say you have one broker, and that one broker has 40 threads. If you have 40 queries running that are all going to take, let's say they're just doing really long running reports, big reports, they're not going to be sub-second, they'll take maybe a minute each. That would tie up all 40 for a minute if you have 40 running at the same time. And that means that regular queries, interactive queries cannot run. They'll have to queue up and wait, and then they may time out. So how do we approach this? We approach this with reserving some capacity for high priority queries. So if you look at this diagram shows the query scheduling system that was added in Druid 018. So it used to be that Druid server HTTP num threads, the outer box here on the scheduling diagram, was completely Wild West. Any query could run on it. It might not even be a query, because the broker server threads do things other than queries. They also respond to health checks. So another issue is that if a broker was full up on queries, it would actually stop responding to health checks as well. They respond to health checks, they respond to metadata requests, they do various things that are not just queries. So one level inside, nested within server num threads, is the query scheduler num threads now. This is a new configuration. And this new configuration is the total number of queries that can be served. Its purpose is you generally want to set it to 1 or 2 lower than the server HTTP threads to ensure that there's stuff left over for health checks. And then another new parameter, Druid query scheduler max low % is the max number of query threads that can run in the low priority lane. That is the most. So that's the most that low priority queries can use. And whatever is actually, I think that this diagram might need to be reworked a little bit, because the reserve capacity is really what's not in that max low %. And the stuff that's not in the max low % is reserved for high priority queries. I guess if you think about max low % as being, let's say it's 20%, if you think about 20% of that being filled in, then the reserve capacity is the high priority capacity. Let me talk a bit about what happens to queries based on whether they're high or low. So if a query comes in and it's high priority, it can actually run anywhere. It can run anywhere, and that's great for that query. Good job, that query. If it comes in and it's low priority, it can only run in the low priority lane. And if the low priority lane is full, then I believe what happens today is that query will get rejected and the client's expected to try it again later. You'll get a special HTTP status code. I don't recall what it is, but it's in the documentation. You'll get a special HTTP status code that says, that indicates that it was rejected due to not having spare capacity to run your query, and you should try again in a little bit. And let's see. So let's talk about how we can decide what's high and low priority. That's the big question. How do you actually decide which queries are the ones that get to use this special fast lane? Which queries have to slum it with the schlubs? So there's one more new config called the laning strategy. The default laning strategy is none. So by default, this feature is disabled, like a lot of new features. We may enable it by default in the future when its performance has been better characterized and its behavior has been better characterized, but we usually start things like this off as opt-in. So it's opt-in. There's two others implementations that we shipped with. One is high-low based on priority. So the idea here is that the user sets a priority, caller sets a priority. Anything above 0 is high, anything 0 or less is low. 0 is default, so by default it's low, but if you set it a little bit higher, it's high. And the third is manual, which is that the user will, the caller, the person who makes the query, will specify the lane it's going to go in as part of the query context. So rather than being based on the priority, they just explicitly say whether which lane is going to go in. That can also make sense. The idea about these two options is the high-low one is designed to integrate well with folks that are already using Druid query priorities, and the manual one is designed mostly for fancy special setups where you have some special logic that's going to be deciding what lane to put things in, and you've configured lanes a certain way. So yeah, so the goal of this feature is to make it so these interactive queries in Druid are always going to be high performance, even if there's a lot of non-interactive queries happening on the same cluster. In a world of fixed resources, in a world where you don't have an infinite sized cluster, you have to do that by deciding who's going to get those limited resources, and we're going to ensure that there's always resources available for interactive queries.